The diversity of space objects scattered across vast expanses of the universe can't but amaze. With some of them barely visible against the dark background of the cosmos, others can easily be observed billions of light years away. Gravitationally bound in space, they form unique elaborate structures, such as planetary systems, star clusters, or galaxies. Today, we're going to visit some of the most exciting ones. First of all, we'll drop in on some remarkable systems within 50 light-years from the Earth. After that, we'll set out to see Westerland 1, which will be followed by a tour around the most horrifying planets known to science today. After leaving the Milky Way, we'll check out several unusual galaxies. This detour will be followed by a visit to practically the very edge of the universe to a remote micro-quasar dubbed SS433. The return trip home will be a long one, and we'll have plenty of time to ponder the question why the universe is the way it is now. What lies at the basis of its laws? And how would it be different if the values of the fundamental constants were different from the ones we know? The anthropic principle may well supply answers to these tricky philosophical questions. Ready? Let's get to it.
Cosmo.
The first in outer space. There are approximately 1,400 stellar systems in space within the radius of 50 light-years from the solar system. Some of them are multiple and contain 2 and more objects, which makes the overall number of our stellar neighbors over 2,000. These are all sorts of stars, from dim red dwarfs to dazzling giants whose temperatures are beyond our imagination. The incredible scale and great abundance of space objects in all their diversity can't but amaze. Life's too short to give account of each and every one of them. Right now, we're going to travel at incredible speeds, by far faster than the speed of light. It will take us just a few minutes to cover dozens of light-years of space. We'll get to check out quite a few remarkable space objects around the solar system. Other worlds and stars are already waiting. After we fly around Proxima Centauri, a detour of 11 light-years that would have passed in the blink of an eye, we're in the environs of the dim red dwarf known as Ross 128. We can't see it from the Earth with the naked eye. Unprepossessing though it may seem, there is an Earth-like exoplanet dubbed Ross 128b orbiting this star. This exoplanet is one of the closest to us. Unlike the yet closer and cooler Proxima Centauri b, the temperature on Ross 128b is relatively moderate, ranging from -60 to +21 degrees Celsius. Assuming its surface to be identical to that of our planet, which absorbs 70% of the light shed on it, the equilibrium temperature of Ross 128b is estimated at around 7 degrees Celsius. It is 8 degrees cooler than that of today's Earth, but quite enough to sustain life. The exoplanet's mass is roughly 35% bigger than that of the Earth. The radius hasn't been accurately measured at this point, but provided the planet's composition is similar to our Earth's, its diameter is supposed to be roughly 10% bigger than that of the Earth. The freefall acceleration on its surface is expected to be just 12% bigger than that on our planet. If all these estimations are correct, then the conditions on the surface of Ross 128b are supposed to be comparable with those on the Earth. Besides, the system is rapidly moving to meet the Sun. In just 79,000 years, it will be closer to us than Proxima Centauri, which is moving away from us. Quite like most exoplanets we know of, Ross 128b is located quite close to its host star. The distance from it to the center of the system is just 0.05 astronomical units, or 20 times shorter than the distance between the Earth and the Sun. It takes the exoplanet slightly under 10 days to complete a full orbit around its star. It is also thought that it must be tidally locked. Speaking about its host star, Ross 128, its mass is approximately 17% that of the Sun, with the radius measuring around 0.2 that of the Sun. The star's surface temperature is twice as low as that of the Sun, at 3,192 Kelvin, and its luminosity is roughly 300 times lower than that of the Sun. It's worth mentioning that Ross 128 is a comparatively quiet star. With its luminosity quite stable and regular, it hardly ever flares up or emits stellar matter, so pernicious for all living things. Moving on through space, 12 light-years in the direction pointing away from the Sun, we will see Lytton's star, also known as GJ273. It boasts one of the largest planetary systems detected in the space nearest to us. The star itself is a red dwarf of an orange hue, whose mass is just 25% that of the Sun. Its radius is 3 times smaller than that of the Sun, and its luminosity is 435 times lower, so it's hardly surprising that it can only be seen through a telescope. It is quite an exciting star, because there are as many as 4 objects detected in its environs, 2 of which are confirmed exoplanets. The other 2 are still prospective candidates, awaiting confirmation. The first confirmed exoplanet was dubbed Lytton B. It was detected thanks to high-precision measurement of the star's proper motion. The object's mass is estimated to be about 2.89 times that of the Earth. Its radius is 35% bigger than that of our planet. This makes the object a super-Earth, and its surface gravity may turn out to be suitable for humans. The distance between the system's center and Lytton B equals roughly 0.1 astronomical units, although the amount of light received by the exoplanet from its parent star is comparable with that received by us from the Sun. Thus, Lytton B lies in its star's habitable zone and may well be considered a potential candidate for searching for alien life. The equilibrium surface temperature of the planet is 259 to 292 Kelvin, or -14 to +19 degrees Celsius. This makes the conditions on Lytton B quite suitable for humans. The other confirmed exoplanet in the system is Lytton C. With this space object's mass similar to that of the Earth, it lies much closer to its host star. The exact parameters of its orbit haven't been defined yet, but it is known that it takes the object just 4.7 days to complete a full orbit around its system's center. It is likely that this is a scorching hot and harsh celestial body without any atmosphere, with one and the same side facing the star at all times. The 2 other objects in the system were discovered in 2019 and are still awaiting confirmation of their status. According to preliminary estimates, they are ice giants with masses from 5 to 15 times that of the Earth. With the radii of their orbits lying within 0.8 astronomical units, their orbital periods cannot be over 558 days. Lytton is a relatively cold star, and with these 2 objects lying beyond its habitable zone, their temperatures are almost certainly extremely low. It goes without saying that at this stage, these 2 candidates still want further exploration. Moving on and away from the Lytton system, we will come across a star known as Altair. Lying 16.8 light-years away from the Earth, it is a bright, white-blue star. Its mass is around 1.8 that of the Sun, and its age is estimated at around 1.2 billion years. This star's luminosity is 11 times that of the Sun, which makes it one of the most conspicuous objects in our night sky. Another curious feature of Altair is its rotation, which is remarkably fast. Thus, it spins on its axis approximately 67 times faster than the Sun. It completes a full rotation within slightly less than 9 hours. The velocity of star material at the equator equals about 286 kilometers per second. Due to this outstandingly rapid rotation, the star's shape is far from an ideal sphere. The star's equatorial diameter is 22% bigger than the distance between its poles and is roughly twice the diameter of the Sun. The star's shape can't but affect its temperature and luminosity, which also differ in its different areas. The stellar matter in the equatorial zone of the star is noticeably colder and darker than in the poles. The temperature at the equator is just 6,900 Kelvin. The poles, meanwhile, are as hot as 8,500 Kelvin, which is around 8,200 degrees Celsius. Interestingly, the fact that Altair has an irregular shape was first arrived at following theoretical calculations. Only later, in 2007, was it finally confirmed after an image of the star was produced. where it is seen to have a disc-like shape. Actually, Altair happened to become the first star beyond the solar system whose surface had been imaged. Unfortunately, no planet has been detected in Altair's environs. Still, observations show rings or a fog of gas enveloping the star. Altair's light is dispersed in these structures, which produces a curious effect. This major interference of light results in a humongous rainbow around the star. On the downside, however, even though it looks fascinating and majestic, it partly conceals the star and so greatly hampers studying it. As we carry on our way through space, we will get as far as Fomalhaut. Lying 25 light-years away from the Earth, this stellar system consists of 3 components. For a long time, the 3 components making it up used to be considered mutually independent space objects. Then, in 2013, evidence showed that they are in fact gravitationally bound, forming a large and single structure in space. Fomalhaut is probably the widest multiple star system located close to ours. The biggest distance between its components reaches 3.2 light-years. Incidentally, almost 11 lunar disks may be placed in our night sky between the remotest objects in the Fomalhaut system. The largest, most well-known and well-seen component of the system is referred to as Fomalhaut A. It's a young and hot star whose mass is 92% bigger than that of the Sun, with its radius measuring around 1.85 times that of the Sun. It was this star that people have referred to as Fomalhaut since ancient times, quite unaware of the fact that there are other, not so easily observable components in this system. The star's luminosity is remarkably high, at 16 times that of the Sun. Its temperature is estimated at roughly 8,500 Kelvin or 8,200 degrees Celsius. Fomalhaut could be as old as 400 to 480 million years. According to today's models of stellar evolution, the star may grow to be around 1 billion years old. On reaching this age, it will more likely than not go supernova and turn into a white dwarf. Fomalhaut A is surrounded by a disk of protoplanetary gas and dust. Divided into several segments, its inner radius is 133 astronomical units, with a width measuring about 25 astronomical units. This disk is thought to be an active stellar nursery, with celestial bodies regularly born there. That is why it is an area of keen interest for astronomers. It used to be thought that there was a massive planet lurking somewhere in Fomalhaut's environs. It was even given a name, Dagon. However, further observations showed that there was hardly any planet there after all. It must have been a wide cloud of dust that was taken for an exoplanet. It would have originated on collision of asteroids and comets. 0.9 light-years away from the main component of the system, there lies Fomalhaut B, also known as TW Pisces Austraini. It's an orange dwarf with a mass around 70% that of the Sun, with its radius roughly 63% that of the Sun. The star's surface temperature is estimated at approximately 4,700 Kelvin, which is 4,400 degrees Celsius. Interestingly, the star's luminosity is much lower than that of the Sun. Our host star is 5 times brighter. In 2019, on carrying out spectral and proper motion analysis, scientists put forward a suggestion that there might be a celestial body as heavy as 0.6 to 1.9 Jupiter masses orbiting the star. The existence of this body still remains to be confirmed, and its exact orbit's parameters calculated precisely. At this point, preliminary estimations show that it should take the hypothetical planet 25 years to complete a full orbit around its host star. The third star in the Fomalhaut system is LP 876-10. It is a red dwarf lying 2.5 light-years away from the main component of the system. The star is 5 times lighter than the Sun, and its surface temperature is slightly over 3,100 Kelvin. It takes LP 876-10 approximately 20 million years to complete a full orbit around Fomalhaut A. Apparently, the red dwarf would have orbited its big brother just 22 times since the birth of the system. As for planets or exoplanet candidates, none of these have so far been detected near the star. Still, observations allow us to suppose that there is a cloud of gas and dust around it, whose radius is anything from 10 to 40 astronomical units. Our next and final destination for today is 37.3 light-years away from the Earth. That's the distance we would have covered now to reach Arcturus, the brightest star in the northern hemisphere and the fourth brightest star in the night sky. The star is the main component of a binary star system. It is an orange giant whose life is now slowly drawing to a close. Most of its hydrogen has already been transformed into helium, and now the star is busy burning the remains of its stellar fuel and gradually expanding in size. Arcturus is also the brightest star of a great stellar stream named in its honor. This gargantuan structure is in fact the debris of a dwarf galaxy absorbed by the Milky Way some 2 billion years ago. It contains 53 stars. Most of them are old and dim and not nearly as impressive as Arcturus. Arcturus emits 170 times as much luminous energy as the Sun, although its surface temperature is much lower, at just 4,251 Kelvin. It is thought that this giant used to be quite like our Sun because its mass is just 10% bigger. But what with the inevitable depletion of its stellar fuel and the inner pressure of its scorching hot plasma, the star turned into an orange giant whose radius is now 25 times that of the Sun. According to today's theory of stellar evolution, this is something that our Sun is expected to go through in the distant future too. Arcturus's age is gauged at anything from 6 to 8.5 billion years. It is hard to predict when it will go supernova at the end of its life cycle, but it will happen quite soon in astronomical terms. Shedding its outer layers, Arcturus will become a scorching hot white dwarf, destined to slowly cool off in the course of billions of years to follow. The second component of the system is barely visible against the background of its giant companion. This small star with luminosity 20 times lower than that of Arcturus lies so close to it that it's hardly possible to define its parameters. Even if some planets did manage to form in this stellar system, many millions of years ago they must have been absorbed by Arcturus itself. Either way, no objects have been detected in the star's environs at this point. A star cluster is a group of stars which formed from one and the same gigantic cloud of interstellar matter. These stars are practically identical in terms of their chemical composition and age. The system they form is bound by gravity forces. Star clusters fall into either of these two categories, which are the main varieties, open and globular clusters. Open star clusters are products of stellar nursery's evolution. The latters are areas of cosmic gas where stars are actively born. That is why the clusters here are mainly comprised of young stars and great amounts of interstellar hydrogen. Gravity forces between them are comparatively feeble, which leads to an open cluster's disintegration several 100 million years after its formation, which of course is mere seconds in astronomical terms. Some of its former members still stick together in their joint movement in space, thus forming a stellar stream, while others break away from their group to become sole masters of their own destiny. Over 1,100 open star clusters have been pinpointed in our galaxy, and incidentally, it appears to be just a tiny portion of their overall count. Globular clusters are larger and denser than open ones, and consist of old and not very massive stars. The average distance between the stars there is 4 to 6 light months. As for their masses, these may reach 1,000,000 times that of the Sun. The Milky Way contains not less than 150 star clusters of this type, and the Andromeda Galaxy over 500. Open clusters are comparatively modest in size, but the star count in some of them reaches thousands. These objects are referred to as superstar clusters. The largest of them are thought to eventually turn into globular ones. All it will take is waiting around for a few billion years or so until the most massive stars there have burned out and exploded. One of the largest superstar clusters in our galaxy is one referred to as Westerlund 1. It was spotted back in 1961 by Swedish astronomer Bengt Westerlund, but for a long while remained largely understudied, as it is quite difficult to observe. The distance from the cluster's center to the solar system has been estimated at approximately 10,000 to 15,000 light-years. Staggering though this figure may seem, Westerlund 1 is in fact one of our closest superstar clusters. That is why it is crucial to observe it, to bring our understanding of stellar evolution processes to a whole new level. The diameter of Westerlund 1 measures around 7 light-years. Astoundingly, this area, which is really tiny in astronomical terms, is literally crammed with thousands of stars with a total mass of about 63,000 solar masses. Some straightforward calculations show the distances between the major members of the cluster are just several light months. As for binary system components, they are much closer to each other than that. Due to incredible density of the stars in the cluster and the clouds of interstellar gas the stars are shrouded in, it is impossible to distinguish the exact sources of light here, as the thousands of stars this light comes from are too densely packed. This greatly interferes with observations and doesn't allow the observer to count the stars. That is why the exact star count in Westerlund 1 remains to be gauged. Among them, the following types of stars have already been pinpointed: 6 yellow hypergiants, 4 red supergiants, 24 Wolf-Rayet stars, and a supergiant with a highly peculiar emission spectrum. Supposedly, it formed on collision of 2 massive stars. In addition, there is a great number of hot blue giants and an X-ray pulsar discovered among the stars in the cluster. The pulsar is an anomalous object, a neutron star spinning with a mind-boggling speed. The binary star count is also quite high in Westerlund 1. This fact may be accounted for by the high density of the cluster's objects. All the superstar cluster's objects are posited to have formed at around one and the same time. However, depending on the type of stars, they differ in terms of their age too. To start with, according to today's theory of stellar evolution, red supergiants cannot be younger than 4 million years. Wolf-Rayet stars, on the other hand, which are in the final stage of their life cycle by definition, are remarkably numerous in the cluster. Their life expectancy is known almost never to have been over 5 million years. Thus, the age of Westerlund 1 is quite accurately estimated at a mere 4 to 5 million years, which in essence is seconds in astronomical terms. At approximately the same time it was forming, first Australopithecus and saber-toothed tigers roamed the Earth, and all that had been left of dinosaurs by then was just their fossilized remains. Mathematical modeling of the cluster's formation shows that the cluster may have contained 50 to 150 heavy stars that would have depleted their resources by now, and so would have come to the final stage of their life cycle. Given the estimates are correct, on average there would have been supernovae every 10,000 years in the course of the past million years. As we know, the heavier a star, the faster it comes to the end of its life cycle and goes supernova, after which it leaves a black hole, neutron star or white dwarf. However, to date only one object like that has been detected. It is thought that many supermassive stars would have turned into black holes, but these are rather difficult to spot today. The superstar cluster Westerlund 1 contains one of the largest stars known today, designation Westerlund 126. Since it is rather difficult to observe it, its radius has been gauged at roughly 1,500 to 2,500 times that of the Sun. If its radius is closer to the bigger margin, Westerlund 126 may be the biggest star known to mankind. However, the radius is more likely to lie closer to the lower margin and measure slightly over 1,500 times that of the Sun. Even so, if its center were to be theoretically placed in that of the Sun, Westerlund 126 would cover all the planets, reaching as far as the orbit of Jupiter. The supergiant's luminosity is approximately 380,000 times that of the Sun, although its surface temperature is comparatively low, just around 3,000 Kelvin. The star's mass hasn't been gauged yet, but today's perception of stellar evolution allows us to assume that it may be around 20 solar masses. Another unusual object in the cluster is a magnetar with a name like a tongue twister. It is also the most powerful source of X-ray radiation in that area of space. Located approximately 16,000 light-years from the Sun, it is a neutron star, whose rotation period is about 10 seconds. Incidentally, this is rather slow in comparison to other objects of this class. Those rotate several times a second. Given that all the stars in the cluster formed at around one and the same time, it would have taken the star that was the progenitor of this magnetar just 5 million years to deplete its thermonuclear fuel. This means that when it was born, its mass should have been not less than 40 solar masses. However, in that case, it should have left a black hole rather than a neutron star after going supernova. It transpires that the progenitor star had to unaccountably lose up to 95% of its mass before going supernova. One of the possible answers to this riddle may lie in the fact that the object may have originated from a binary star rather than a single one. By spinning around their common mass center at an astounding rate, the system's components had a chance of actively exchanging material. At some point, the supernova would have scattered most of this material in the space around it, while the second component would have been ejected from the system. The star Westerlund 1-5, which is located comparatively close to the magnetar, may well have been that very component, although it is not certain. Unfortunately, chances of discovering any planets in the superstar cluster Westerlund 1 are thin. First of all, the stars the cluster is comprised of are too young for any planets to form in their environs. This curious process takes hundreds of millions of years at the very least. Secondly, even billions of years later, when the cluster supposedly turns into a globular one, it is hardly worthwhile to anticipate any objects to be born there that would potentially be capable of sustaining life. The close proximity of large and heavy stars makes the potential planet's orbits unstable. Moreover, in certain circumstances, a massive neighbor relatively close to a star system may actually destroy it completely. Besides, thousands of active stars concentrated in a small area of space create a remarkably powerful radiation background. Frequent flares of supernovae occurring in this crammed space may cause harmful gamma-ray bursts which destroy any life on a planet's surface. Chances are that even if mankind finds a way to cover interstellar distances, clusters will still remain deadly areas for quite a while. Shortly before Halloween in 2020, NASA compiled a list of the most terrifying worlds. Among others, they included 6 exoplanets. Each of these objects' environments is not just extremely harsh for any living organism, even finding oneself in their comparatively close proximity may prove to be fatal. The first object on the list is a black gas giant, designation TRES-2b. This celestial object orbits the star TRES-2, which is a yellow dwarf lying as far as 718 light-years away from us. Let's take a closer look at it. Due to some unique properties of the chemical composition of the surface of TRES-2b, the planet absorbs over 99% of all the light shed on it. The nature of these properties remains a mystery, and chances are there are some chemical reactions taking place on the surface that we have never registered on any similar object before. And it is these properties that make TRES-2b the darkest exoplanet on the astronomical map of today. This gas giant was discovered on the 21st of August 2006, with more details on its characteristics obtained several years later. The mass of TRES-2b is 1.2 Jupiter masses, and its radius measures 1.27 times that of Jupiter. The atmosphere is as scorching as 1000 degrees Celsius, which gives the exoplanet a faint red glow like that of embers. Still, in spite of its gloomy looks, TRES-2b doesn't really qualify to be called the most dangerous place in the universe. There are many more objects lurking in space that are more terrifying than that. Let's see some more inhospitable ones. Here is another exoplanet, designation 55 Cancri E. It lies in the system of a Sun-like star, designation 55 Cancri A. This celestial object was discovered on the 30th of August 2004 by the Doppler spectroscopy method. Let's look at it in more detail. The planet's mass equals approximately 8 Earth masses, and its radius measures 1.875 that of the Earth. 55 Cancri E is tidally locked, and so it is always daytime on one side and nighttime on the other. That is why the side facing the host star is always heated up to a temperature reaching 2400 degrees Celsius, with the temperature on the night side 1300 degrees Celsius. These values are so high because the distance between the planet and its parent star is just 0.0183 astronomical units. Besides, volcanism on 55 Cancri E, which is thought likely to be there, causes dust clouds emissions. These clouds trap heat and effectively prevent it from escaping into space. The planet's orbital period is slightly under 18 hours. As for the atmospherical makeup, there is helium and hydrogen registered in it. There are also large amounts of carbon. Incidentally, this element is likely to form thick layers of graphite and diamonds in the planet's interior. 55 Cancri E isn't the only object in the planetary system of its host star. There are 4 other celestial objects orbiting it. The environments on these are by far more hospitable, which is the feature by which the 55 Cancri A system differs from the following object. It is dubbed Poltergeist, or PSR 1257 plus 12c. This is an exoplanet lying in a pulsar system. The celestial object is located just 0.36 astronomical units from the system's center. This shows that Poltergeist wouldn't have survived a supernova that must have taken place before the pulsar had been formed. Consequently, the exoplanet is likely to have formed after this tremendous event, with the material for it coming from the nebula left after the explosion. According to another hypothesis, the pulsar may have formed after the merging of 2 white dwarfs. Unlike with a supernova, this process isn't always accompanied by a powerful blast. Still, as this is the first object of its kind we have discovered, science cannot give a definite answer as to its origins. The system with the celestial object lies 2,300 light-years from the Earth. Its mass is approximately 4 times that of our planet. As for its orbital period, it is around 66 days. Incidentally, the outstandingly powerful radiation emitted by the pulsar is enough to crumple any spaceship wanting to approach the mysterious exoplanet in its system. Even with all these properties taken into account, Poltergeist does not really qualify as the most dangerous exoplanet known to us. On approaching it, an astronomical body may simply get destroyed, but it would get positively vaporized in close proximity to the following object. The reason for this effect is the extremely high temperature on Kepler 70b, which is the hottest exoplanet known to us. The object orbits the subdwarf star Kepler 70. With a surface temperature higher than that on our Sun, it reaches 6,800 degrees Celsius. The object's mass equals 0.44 Earth masses, and its radius measures 0.76 that of the Earth. The celestial object's orbital period is 345 minutes. In other words, a day here is less than 6 hours long. Interestingly, the exoplanet regularly passes another object in the system, Kepler 70c, at a distance of 240,000 kilometers. To date, this is the closest that planets in space have been registered to pass each other. The extremely high temperature on Kepler 70b could be accounted for by the fact that this object may once have been part of its parent star. As for giving it the status of an exoplanet, it will take more evidence to confirm that it deserves to be given it, so this remains an open question. It should be mentioned that Kepler 70b is not the only celestial object we know of that interacts with its parent star so closely. Another object in similar conditions is the exoplanet known as WASP-12b. This celestial body lies 870 light-years away from our system. Its radius measures 1.93 times that of Jupiter, and its mass equals 1.46 Jupiter masses. WASP-12b is just 0.03 astronomical units away from its parent star. Due to this close proximity, the exoplanet has a temperature reaching as much as 2,200 degrees Celsius. The host star's extremely powerful gravitation slowly absorbs WASP-12b. Eventually, in approximately 10 million years' time, the exoplanet is expected to be destroyed completely. Bearing all this in mind, we will probably never delve any deeper into the nature of this exoplanet. It would appear that studying worlds of this kind cannot be high on scientists' list of priorities. However, some of these objects may happen to have some really unique features. Seemingly quite plain and ordinary, worlds like that may conceal many more dangers than would appear at first glance. When flying past the celestial body HD 189733b, for example, one might complacently think it a safe planet, as it resembles our Earth by its looks. But if one were to get as low as the level of its atmosphere, one would be exposed to some life-threatening dangers. For a start, the object's winds carry particles of silicate and develop velocities of 8,700 km per hour. Besides, the rains on this planet cause precipitations of molten glass. The reasons for such hazardous weather conditions are extremely high temperatures and the atmosphere's peculiar chemical composition. Speaking about the exoplanet's orbital period, it is approximately 2.5 days. And it is highly likely that the object is tidally locked to its parent star. As usual, a quick overview of its main characteristics. HD 189733b is a bright blue gas giant orbiting an orange dwarf in the constellation Vulpecula. It lies just 63 light-years away from our system. The object's diameter is 1.1 times that of Jupiter, and as for its mass, it is 113% that of Jupiter. Interestingly, the distance between HD 189733b and its star is 30 times less than the distance between the Earth and the Sun and equals approximately 5 million kilometers. Due to its close proximity to the parent star, it has a constant surface temperature of as high as around 930 degrees Celsius on the day side, with the temperature on the night side never dropping below 425 degrees Celsius. Immediately on being discovered, the celestial body became a subject of investigations. In 2007, thanks to data obtained by the Hubble telescope, scientists found out that HD 189733b has a foggy atmosphere. Interestingly, when the planet transits between the observer on the Earth and its star, its atmosphere assumes a reddish hue. This effect could possibly be caused by the haze in the atmosphere. According to preliminary estimates, it consists of particles of iron, silicates, and aluminium oxide. Apart from that, the information beamed back by the Hubble telescope helped scientists establish that the planet's atmosphere contains water vapor, neutral oxygen, and an organic methane compound. Additional investigations revealed the presence of carbon monoxide on the day side of the planet. What prompted most questions, however, was the results of investigations revealing traces of methane of an unusual variety in the planet's atmosphere. This chemical element was shown to be in a peculiar fluorescent state when it emits electromagnetic radiation in the infrared range. This state of the substance is indicative of some unknown activity in the atmosphere of the exoplanet, which still remains to be found out. This is quite a clear-cut example of a situation when investigating an object like an exoplanet with an exceptionally harsh environment may yield unexpected results about some processes taking place there that will be a valuable contribution to science. And as the process of studying these worlds continues, they will remain no other than horror planets to us, as well as a solid reminder that we're more than just lucky to be the dwellers of our Earth. Distances from the Milky Way to other galaxies are by all accounts mind-boggling. As a rule, it is anything from millions to billions of light-years. Due to the universe's cosmological expansion, the distance between the Earth and any remote object in the universe is constantly growing, which makes the light emanating from this object look redder than it actually is. This phenomenon is known as a redshift. It is of great help in gauging distances and velocities on the astronomical scale. Alternatively, some galaxies' spectrum is blue-shifted, which means that they are not on an escape trajectory from us, but on the contrary are moving to meet us. One of these unusual space objects is the galaxy M86 in the Virgo cluster. Roughly 52 million light-years away from the Sun, it is moving towards the Milky Way at a speed of around 244 km per second, which makes it one of the fastest-moving blue-shifted galaxies. By moving at a high speed through the scattered gas the Virgo cluster is filled with, M86 is constantly shedding its own interstellar matter. As a result of this process, it leaves a trail of long lines of warm ionized hydrogen behind. M86 is connected with the almost destroyed spiral galaxy NGC 4438 with several of these filaments. These two galaxies are thought to have collided at some point in the distant past, which was the smaller one's undoing. Interestingly, M86 is known to have destroyed its other neighbors in the past as well. Several stellar streams have been detected in its halo that are likely to be the remains of smaller galaxies absorbed earlier. An impressive number of globular clusters in its structure is another outstanding feature of M86. Observations show that their number is upwards of 3,800, which is around 25 times as many as in the Milky Way. There is a theory that claims these clusters to be the remains of dwarf galaxies that M86 would have absorbed in the past. If it really is the case, then it would have destroyed tens or even hundreds of other galaxies. Having said that, M86 looks anything but unique. The galaxy ESO 137-001, which we'll be looking at next, has a similar shape. But unlike M86, it appears more outlandishly original. Located 227 million light-years away from the Sun, it is as heavy as 5 to 14 billion solar masses. As for its stars, most of them are young and bright blue giants. ESO 137-001 in its turn is part of Abell 3627, a large galaxy cluster. Moving to its center at an incredible speed of almost 2,000 km per second, the galaxy collides with interstellar gas pressure inside the cluster. As a result, its own gas is blown out, leaving behind tails that stretch for up to 260,000 light-years. Incidentally, the mass of interstellar gas in those areas is 2 to 4 times that of the gas inside the galaxy. It is hardly surprising that starbursts are a common thing here. That is, stars don't stop forming in these enormous streams made up mostly of hydrogen. When seen from the side, ESO 137-001 appears like a giant jellyfish floating through endless expanses of space. Unfortunately, as the galaxy is continuously stripped of its interstellar gas, its life expectancy diminishes too. With not much material left, no new stars can form here, which greatly affects the structure of the spiral arms and central bulge of the galaxy. On the bright side, scientists have a chance of finding out more about dark matter and its interaction with other space objects by observing the behavior of the gas streams left in the galaxy's wake. Speaking about the formation of new stars, there is a galaxy with a name that speaks for itself: Baby Boom. Around 4,000 stars are born here every year, which is about 400 times more than in the Milky Way. Straightforward calculations show that on average, a new star lights up in this area of space every 2 hours. The Baby Boom galaxy lies around 12.2 billion light-years away from the Earth. This means that what we see when observing it is what was happening just 1.5 billion years after the hypothetical Big Bang. It was a time when the universe was still in the process of forming its structure. What is taking place in the galaxy now is drastically different from what we expect to observe there in theory, based on what we know about star formation. The reasons why stars are produced here at such an astounding rate are not known yet, but it is beyond any doubt that Baby Boom is able to provide us with a lot of information about the early stages of our universe's evolution. One of the few galaxies one can observe through an amateur telescope is the so-called Sombrero Galaxy, official designation M104. It lies 30 million light-years away from the Sun, and its diameter is roughly 4 times smaller than that of the Milky Way. The Sombrero Galaxy's outstanding feature is a massive ring of dust and cold hydrogen enveloping it. Observations show that it is here that most young stars are born. In addition to the peculiar ring, the Sombrero Galaxy is also remarkable for its elaborate inner makeup. Observations with the Spitzer Space Telescope show that most stars in this galaxy form a structure typical of elliptical galaxies. The stars here are mostly rather old yellow and red dwarfs. The other stars here, on the other hand, form spiral structures concealed within an elliptical cloud. It is thought that this phenomenon is a result of two galaxies' collision, with their stars subsequently and almost inevitably mingling together. It is incredible that the galactic structures survived a merge of that scale with minimal damage, are none the worse for this tremendous collision, and can still be observed. Another peculiar feature in the Sombrero Galaxy is exceptionally powerful X-ray radiation emanating from the center. It is assumed that the accretion disk of a supermassive black hole may be its source. The mass of the hole is estimated to be over 1 billion solar masses, which makes this enormous object one of the most massive black holes known to science today. There are also several sources of tremendously high frequency or terahertz radiation detected within the galaxy, although today their nature is still a mystery. Our galactic parade today is concluded with yet another object boasting an elaborate inner structure, the eerie M64 Galaxy, rather aptly dubbed the Black Eye Galaxy. The nickname comes from a dark band of cosmic dust that partly conceals the galaxy's center from the observer on the Earth. Due to this line of cosmic dust, as well as the exceptionally bright active nucleus, it is impossible to estimate the Black Eye's number of stars even roughly. What we do know is that it is comparatively small and not so remote. Its radius measures 25,000 light-years, and it lies approximately 17 million light-years away from the Milky Way. The Black Eye Galaxy is made up of two well-defined parts. Interestingly, the inner disk with a bulge rotates in the direction opposite to that of the outer ring. The most likely explanation for such a bizarre makeup is that the galaxy formed after two smaller ones collided and merged in the distant past. Admittedly, it would take a combination of a number of mutually independent factors for such a fascinating and well-defined structure to form. For example, the progenitor galaxies would have moved at specific velocities and come together at a certain angle. The odds of a success would have been minuscule. As a rule, microquasars are X-ray binaries, that is, stellar systems made up of two components. One of them is a regular star similar to our Sun. The other component is a compact object like a black hole or a neutron star. Matter in such microquasars is constantly in the process of accumulating in the compact object, which is accompanied by occasional outflows of matter at great speeds. These outflows are known as jets, and the nature of these jets reminds one of processes taking place in regular quasars. Now, it is not a regular occurrence in ordinary quasars. Meanwhile, as the mass of a microquasar is smaller than that of an ordinary quasar, jets may originate here practically on a daily basis. The principal difference between microquasars and ordinary quasars is in their mass and the frequency of matter outflows. For example, the mass of the compact components in microquasars is considerably smaller than the mass of those in regular quasars. It is just several solar masses. Just to compare, the average mass of a supermassive black hole in the center of a quasar may be approximately as much as 100 million solar masses. As for the mass of the black hole likely to be found in the center of SS433, it must be just a few dozen solar masses. The accretion disk of a microquasar is intensely luminescent, with emissions in the optical and X-ray bands. A regular quasar is an astronomical body boasting the highest luminosity among other objects in the observable universe. According to contemporary scientific views, These celestial bodies are active cores of galaxies where a supermassive black hole sucks in matter all around it, thus forming an accretion disk. As for the disk itself, it is a source of very powerful luminosity. Just to give you an idea, its luminosity may sometimes be hundreds of times as intense as that of all stars in a galaxy like ours combined. To date, over 200,000 quasars have been identified. We're able to observe some of these quasars in the sky even without using a telescope, and so the rate of discovering new objects of one or the other category is another principal parameter by which regular quasars and microquasars differ. If we look at the list of known microquasars, it contains just a few entries so far. The first microquasar was discovered back in 1978 when a source of unusual radio and X-ray emissions was detected by two astronomers from the University of Cambridge as they were looking for debris left over from supernovae. Detected in the constellation Aquila, this source was later dubbed SS433. The object under scrutiny is an eclipsing X-ray binary system. One of its components is likely to be a black hole. As for the second component, it is a star of spectral type A. That is, a main sequence dwarf star of a whitish hue. It is assumed that this star's mass is 10 to 30 times that of our Sun. And more likely than not, the dwarf used to be considerably heavier in the earlier stages of its existence. Its surface temperature is thought to be anything from 7,000 to 11,500 degrees Kelvin. This temperature range is typical for stars of this type. It is actually its temperature that gives the star its pale yellow tint. In fact, if we look at the stars closest to the Sun, then Sirius, Altair and Vega fall into the same class as this star. SS433 is located within the supernova remnant W50, sometimes also called the Manatee Nebula. The age of this nebula is estimated at approximately 20,000 years, and the distance between the nebula and the Earth measures about 18,000 light-years. The jets from SS433 distort the clouds surrounding the W50 nebula. According to a certain theory, the W50 nebula and the microquasar SS433 are actually related, and came to be as a result of one and the same supernova event, which supposedly took place around 20,000 years ago. It takes either of the two objects in the system 13.1 days to orbit the common mass center. In fact, the way the SS433 system works is quite exciting, with both components constantly interacting with each other. Matter from the second component, that is the regular star, flows to the first component, or the primary, supposedly a black hole, thus forming an accretion disk around it. As it spirals, the matter heats up to extreme temperatures and emits X-rays. Some part of this matter leaves the system in two jets at the rate of approximately 26% of the speed of light. That is 79,000 kilometers per second. In 2019, thanks to the ALMA observatory, astronomers managed to get detailed images of SS433. It was clear from the emission structure that the microquasars' jets themselves are rather narrow, and their shape is irregular and has nodes. Further studies of the object showed that the shape of the jets is distorted as a result of precession, that is, a process when the jets slowly rotate on their axis as they spiral. The diameter of either of the two jets ejected from the microquasar in two opposite directions measures approximately 5,000 times the diameter of the solar system. As SS433 is relatively close to the Earth, it is particularly valuable to scientists studying the phenomenon of microquasars. Images beamed back by the ALMA observatory showed its jets for the first time, and it also helped establish that the direction these jets point at is never the same. Just like a top, the spinning toy gradually slows down, they too rotate on their axis, which is perpendicular to the plane of the accretion disk. The ALMA images boasted another outstanding feature. The shape of SS433 was predicted in fine detail thanks to spectroscopic measurements that had been done in 2018 using the Global Jet Watch telescopes. And so the actual shape largely corresponds to the new images, where SS433 is really seen to have a shape reminding one of a corkscrew. It isn't a rare occasion when jets like that originate here or there in the universe. As a rule, jets of plasma, also known as relativistic jets, are spewed out of the centers of active galaxies, quasars, and radio galaxies. When this occurs, there are usually two jets as such, pointing in the opposite directions. And this is exactly what we can observe in the case of SS433. Today, the phenomenon of jets like that wants deeper studying. It is believed that jets originate following the interaction between magnetic fields and the accretion disk around a black hole or a neutron star. As for their size, it may be staggeringly enormous. In the case of the radio galaxy 3C120, for example, the jet stretches for at least several kiloparsecs away from its source. It is highly probable that in the future the regular star in the SS433 system will shed its outer layer completely as a result of the influence of the compact object. Its core, meanwhile, will remain hot, and thus the star will qualify to be called a hot subdwarf. Later, the star is to be gradually sucked in by the black hole, and sooner or later, after this process is completed, the SS433 system will assume a classical look. It will comprise just the compact object. The process of this system's evolution will of course continue for thousands of years, so we have plenty of time to study this phenomenon. And while the microquasar SS433 is active, we will have many opportunities to carry out detailed observation that would help us understand the nature of this celestial object. Let's keep in touch. The yellow dwarf, which is known as the Sun and which gives us light and warmth every single second, is located on the periphery of the Milky Way. As it orbits around the center of our galaxy, it follows the so-called co-rotation circle. This means that the rate of our Sun's movement accurately follows the rotation of the galaxy's spiral arms, which are stellar nurseries. Thanks to this fascinating synchronization, the solar system hardly ever crosses the arms, thus keeping a safe distance away from harmful supernova flares and the heat of active stars. The diameter of this galactic orbit matters too. If the Sun were to lie closer to the center of the Milky Way, the great abundance of heavy elements would have rendered the forming planets too large and massive. Besides, the galactic core's powerful ionizing radiation would have thwarted any attempts of life to evolve and propagate on the surfaces of the planets and their satellites. On the other hand, the further from the galactic center, the much poorer the chemical diversity of elements. In this case, rocky planets of a rich chemical composition like our Earth would never have been able to form. The Sun would have been orbited solely by gas giants or icy giants at best. There are some exciting coincidences easily noticeable within the solar system too. For example, consider this. The Earth lies the ideal distance from the Sun and follows a stable orbit with a small eccentricity. Our planet's orbital trajectory is remarkably close to an ideal circle. If the trajectory's diameter shifted as little as 5% in any direction, the planet would either become icebound or would be shrouded in a dense cloud of water vapor. The bottom line is that any advanced life forms would cease to exist. In addition, the Sun itself has a number of extremely important features. It is neither too hot nor too cold, and its life expectancy is considerably long. Even though there forms a wide habitable zone around a hot star, its life expectancy is generally small. Also, its ionizing radiation is much too powerful. Colder stars like red dwarfs, on the other hand, are capable of sustaining a habitable zone too narrow and generally too close to themselves. That is why, more often than not, planets within this zone are tidally locked to their star, and so are not equally heated up, with the temperatures on the two sides drastically different. Someone will probably offer a counter-argument here to this effect. It isn't the Earth that adapted to host humans, but rather life adapted to the conditions already present here. This is a rather sensible point, although if we delve deeper into the structure of the universe, there are some facts that cannot be accounted for by this statement. First of all, it should be mentioned that celestial bodies can have stable orbits only in three-dimensional space. In dimensions other than that, the orbits of electrons in a substance's atoms become unstable. In other words, electrons in atoms either collapse to the core or fly away into space. Thus, atoms cannot exist in a multidimensional space. A universe of this sort would only have radiation and freely floating elementary particles. Another point to consider is that there are several fundamental values that all contemporary physics is based on. They usually include the speed of light, the gravitational constant, the Planck's constant, the elementary charge, and the masses of the electron and the proton. All these values have been arrived at experimentally, and today are considered to be mutually independent. However, modern science cannot say why these values are exactly like that and no other way. It is known that a free electron is a bit heavier than a proton and electron system. Without this inequality, there would be no hydrogen around, because otherwise its atom would immediately turn into a neutron. By the same token, with no hydrogen around, no stars would be able to form in the universe, and heavier elements would never exist either. With the values of the Coulomb interaction and the powerful interaction slightly different from those gauged today, no thermonuclear synthesis reactions in stars' interiors would be possible. With an increased gravitational constant, stars would compress far too strongly. This would inevitably produce a great plethora of large and hot stars with a short lifespan. After they burned out, most matter in the universe would be buried inside black holes and neutron stars, never to become material to help form planets, satellites, and other space objects. By contrast, with a decreased gravitational constant, interstellar gas would not be compressed enough to make thermonuclear reactions self-sufficient. In this case, stars would simply never flare up, and the universe would be filled with giant brown dwarfs this time. A change in the electromagnetic interaction coefficient in any direction would render chemical reactions and complex compounds virtually non-existent. On the other hand, if the Coulomb interaction were stronger than it is now, there would be no elements heavier than boron around. Their nuclei would simply be torn apart by protons' electromagnetic repulsion. Heavy elements can form in the universe thanks exclusively to a number of factors favorably combined. Here are some more exciting coincidences. Consider this. It is thanks to a special state of carbon that helium is able to transform into it. Known as carbon resonance, this phenomenon plays a crucial role in the formation of heavy elements and their spreading across the universe. It is thanks to carbon resonance that stars go supernova and shed their outer layers. Atoms born in their interiors are scattered across space to form planets, satellites, asteroids, and other celestial bodies. Besides, carbon is vital for the genesis of life. Only carbon is able to create long and elaborate chains, forming the base for and forking out into incredibly diverse chemical compounds. Life as we know it can exist only when based on organic compounds that would never have formed but for carbon. So now it is clear that the universe itself, as well as life in it and intelligent observers, that is, humans, came to be only thanks to a number of fascinating and not readily obvious coincidences. Theories that would be able to account for this are usually beyond the scope of physics and are rather to do with philosophy. One of these is referred to as the anthropic principle. Even though the term itself was coined only in 1973, the ideas it is based on had been voiced much sooner. For example, we come across this idea in the works of Soviet scientist Grigory Idlis dating back to 1958, where it is expressed to this effect. What we observe is a part of the universe that is not random a priori, but one that was made suitable for the genesis and evolution of life by its special structure. This vision is referred to as the weak anthropic principle. Much later on, The so-called strong anthropic principle was formulated, according to which the universe is supposed to have certain properties that are favorable for the evolution of intelligent life. Or to put it differently, an observer is needed for the universe to exist. The latter formulation is based on an idea used in quantum physics. The observer plays a crucial role, because their presence dramatically influences the behavior of particles. That is why the observer is indispensable in any quantum physics experiment. We might also see it put this way. The laws of the universe are the way they are because we can exist only in the universe the way it is. The anthropic principle implies that theoretically there may exist other universes out there, or else other parts of this single universe that would have a different set of physical laws. However, it is that either mankind is not able to observe those areas, or those hypothetical worlds cannot get real without an observer. This assumption may be further developed into a multiverse theory, or a hypothesis where basic physical constants may change their values as time goes by. Still, observations of the areas of the universe visible to us show that the fundamental values remain unchanged. The concept of a multiverse defies description in the scope of science. Generally speaking, the anthropic principle lies largely beyond the scope of the scientific view of the world and requires a metaphysical approach. Stanislav Lem commented on this to this effect. It's an attempt to account for the unknown using the unknown. Also, it is evident that the anthropic principle clashes with the mediocrity principle. The latter states that the area of space observable to humans isn't anything extraordinary, and there would be lots and lots of similar stretches within the universe. The Milky Way, for example, doesn't boast any particularly unique structural features, and its position in the large-scale structure of the universe doesn't particularly stand out among billions upon billions of other galaxies. In addition, there is the principle of space homogeneity accepted in contemporary physics, which means that natural laws are really the same from point to point in space. The correctness of this postulate is confirmed by countless observations of the world around us. Mankind has been stirred by these questions since times immemorial. Are we alone in the universe? Is our home planet unique? Or are there more Earth-like worlds in the Milky Way? Or is what we see just a kind of backdrops, with whatever there is behind them being something incredible that would defy our understanding and therefore appears to be carefully concealed from us by the universe? Science cannot give satisfying answers to any of these questions yet. Otherwise, it would probably bring about a downright revolution in our perception of the world and upgrade our cognition to a whole new level. As it is, everyone is entitled to their own personal opinion. Unfortunately, space tours like that will be confined to science fiction for a long time. We're virtually just scratching the surface in space exploration, and the future definitely holds lots and lots of amazing discoveries both in the solar system and beyond. Every new step forward gives answers and prompts yet more questions. And this is the way the ultimate puzzle, the universe, is slowly being put together piece by piece.